I'm ready to get started, so let's do so. I think this is our 10th day. Let's see. This is the 4th week. When we complete this week, that would normally be 12, but we had one day off. So this is the 10th day. That's what it is. We had our first homework assignment. We had rewrites on it. And I want to tell everybody, if you need more time, it's okay. So if you want to keep it for till Friday, that's good. Nothing wrong with that, okay? So I don't feel anything badly about that. But if you're ready to turn in the homework, I'm ready to take it. And then I will give it back to you, graded final version, Friday. So that will be your grade. But if you want to keep and return on Friday, give it to me on Friday, that's okay too. Okay? So I want to start. Does anybody want to hold their paper till Friday to keep working on it? You can. But if you want to turn it in, I'm ready to accept it. Does anybody want to turn in their paper?
I do.
Okay. Okay. Thank you very much. If anybody else wants to turn it in, that's one. In the meantime, just because, I don't know what you're supposed to do with yourself if you don't have any direction. So I'm going to give you some more homework to do.
Thank you.
Thank you. I don't blame you. That's like I was one time pulled over by a policeman and given a speeding ticket, and I said, thank you. And he said, I don't think you said thank you. I almost said, I don't care what you think, officer. Okay, so that's homework 2. I will post this. We've covered the material for you to be able to do homework 2 already. And let's make homework 2 do maybe, let's give ourselves a little bit of a breather. How about next Friday? Not this coming Friday, but the following. Okay? So homework 2 is due on, oh my goodness. Yes. No, that's from Halloween. I'm sorry, I got confused there. I don't know if you guys know what I'm talking about.
No, that's right.
It was?
Yeah.
There was something. I don't remember. Halloween was the scariest movie I ever saw. Okay. So again, if you want to take another little time for homework 1 rewrites, it's okay. If you want to turn it in on Friday, that's good. If you want to come by and ask me questions, I will essentially do the problems with you. Okay? So it's okay. But we can go over things together. I think that's a good learning experience for us. And in homework 1, and partially in homework 2, we're looking at some very we're looking at some very detailed problems. Some problems where I want you to show every step of here's what I'm using to go from one statement to another. And we're kind of being restricted by how little information that we have to work from. Eventually, we're going to be looking at problems where we're going to be saying, well, I know this is true. We're going to have big ideas to be able to push through to get to other big ideas. It won't be so meticulous details of algebraic property of R. Anyway, that's what I want to tell you. We have finished the beginning material for this class having to do with numbers and introducing primarily, the biggest introduction had to do with the absolute value of a real number. And what we're going to get to now is a topic that's going to be a recurring topic throughout the course. So this is a major topic in the course. And that has to do with sequences. Okay. We ended class, if I remember last time, with functions, okay? So we said what a function was. Okay. So here's our topic. So this is chapter 3. That's where we are. So it has to do with sequences. Oh, I'm sorry. Let me back up just a second and recall about functions. So here we have this definition. This is the way I'm going to define it. A function f is a set of ordered pairs So here's what I'm writing. F looks like, A comma B. Okay. And I'm going to write a little bit more here, such that A is an element of A, and B is an element of some set B. And so what it satisfies satisfying if AB1 and AB2 are both in F, then B1 had to be equal to B2. What I want to stand here, and this is the way I'm going to define it, I'm going to say, as a definition, the set A is called the domain of A. And so here's what we're thinking of. We're thinking that
I think you mean domain.
domain of F. Yes, that's what I should say. That's right. Thank you very much. And I really don't like this definition. I want to back up. I don't like what I'm writing. Forgive me. I'm going to write it like this. F given a function F equal to A comma B, such that A is an element of A and B is I don't even like that. I'm just going to write this. Given this, then I want to say this: the domain of F denoted by DOM of F is equal to the set of all A's such that there exists a B with AB being an element of F. So the domain of F is the collection of all first values in the ordered pairs that are in F.
I would assume that we'll have one for the range of F that will look at all the outputs.
Yes, and I'm going to be a little bit more discerning here. And I'm going to say the range of F, exactly what you said, given a function F, element of, not element, but equal to, the set containing A to B. The range of F is denoted RAN of F, and I'm going to say what it's equal to. But I want to back up. I really don't like me putting this A and B in there at all. So in the first definition that I rehashed, I really wouldn't have rehashed it because I put this A and B there, big A and big B. I don't want it there. So if you don't mind, I'm going to make one more change. I don't care whether you mind or not. We're going to write this, okay? So you take away that A element of big A and B element of big B. That's not a good definition. I made a mistake. So that's what I want to put. Okay, so make that change. I'm sorry. Okay, so we're continuing this definition of range, and is given by, so the range of F equals to a set. It's the set of all these such that there exists an A with A, B being an element of F. So it's all the second coordinate values. Now, I'm going to say something called, just verbally, there's something bigger than the range of F that might be of interest. And so we call that a codomain is what it's called. And so it's a set that maybe contains the range of F. And for us, we're going to be looking at functions that grab real numbers or grab parts of real numbers and send them to real numbers. That's what we're going to be looking at, okay? And so the codomain might be real numbers, but the range might be some smaller subset of that. Okay? So that's what we're going to be looking at. Right now, just tell you. Okay. Now we're ready to start with chapter 3, having to do with sequences. And so, what is a sequence? Well, it turns out it's a function. Definition. A sequence is a function whose domain is the set of natural numbers. And whose range is a subset of all. At least that's what we're going to be looking at. We're going to be looking at that type of sequence. So this is an infinite sequence. I'm not writing that word in terms of the definition because what we're going to think of as sequences are infinite sequences. And really it's of real numbers. Okay? But I'm not emphasizing that except in this definition that the range is a subset of all. But those are words that are sometimes included in the definition. I'm not. I'm just saying that some books would include them. Let me give some notation for a sequence. So we often denote a sequence by x of n, n running from 1 to infinity, where x of n is the nth term of the sequence. In terms of usual or normal function notation, so when we think of a function, normally we denote the function by, did I write something goofy? No, okay, it doesn't matter of time. Normally, we write down a function and we label it with a letter. And the most typical letter to represent a function is F for function, okay? And we say F of X. And we think of X being a real number most of the time when we're looking back at our experiences in math. I'm sure that's what you've seen most often. What we're saying for a sequence, we have F of N. Does that make sense? Because the domain is the set of natural numbers, okay? So instead, here's what we're having. We're having F of N, that's our function, but really that's the same thing as X of N, which we're denoting by X sub N. That's the output value. So F of N is an output value, but we're really calling it X of N, okay?
So X of N would be dependent?
Yes, would be the dependent variable, and it would depend on N. Okay, that's the input value. That's right. So this is what we have. Now, often there are formulas that represent X of N. Okay. So the terms of the sequence can be categorized by formula based on N. Often, not all the time, but lots of the times. So I'd like to look at an example. We could have X of N, n running from 1 to infinity, be represented by 1 over N. And so if I were to write this out as a set, what I would get would be the first number. Now remember, I'm thinking N is a natural number. N runs from 1 to infinity. The first number we get out is 1 over 1, which is just 1. And then we get 1 over 2, then 1 over 4, it goes on forever. Is that okay? That's what it looks like.
Just to be clear, the sequence is not a set itself.
No,
right?
no. But it is a set of numbers, and I'm going to write one other word associated to it that gives a good description for a sequence. So, idea of a sequence.
Isn't it because our definition of a function is the set of all inputs and outputs?
Yes, and here, writing it in this way, though, the input's understood to be 1, 2, 3, and that's the corresponding output. And so it's a way of notating it by writing in this way with one other extra word. So the idea of a sequence is a sequence is a countable, ordered set. The countable has to do with being in one-to-one correspondence with a set of natural numbers. So there's the same number of output values that there are natural numbers. And the key word I wanted to represent, or to emphasize here, is ordered. So it's not the same thing as a set, John, because in a set, the ordering doesn't matter. For a sequence, the order matters, okay? So it's an ordered set. It's kind of a loose way of saying it. It's got to have infinite many terms and countably. Okay. So here's what I mean. As an example, if I look at the sequence, minus 1 to the n, okay, that's a sequence, Megan. Tell me what the first term is. What is it, Megan? When n is 1, what do we get out? We sure do. Megan, what's the second term? Nope. Now remember, we're letting n be 2. That's right. Megan, what's the next term? It goes on forever like this. This is a sequence. And let's call this, I'm going to back up a little bit. You have room. I'm going to call this x of n. Okay? Maybe you don't have room. Anyway, is a sequence. So that's a sequence. But in the same example, I want to look at another sequence. So Chuck, let's look at this sequence. So, same example, I'm going to look at the sequence, I'm going to call them y sub n's. And what I'm going to define it to be is minus 1 to the n plus 1. So Chuck, what's the first term of this sequence? When n is 1, what do we get out?
1.
1. What's the next term?
Take the 1. 1. So on, so on.
So it just alternates between minus 1 and 1, and it continues on in this pattern. Now here's the question. Here's what I'm going to make the observation. Note, x of n, in this example, and does not equal to y sub n. Even though both are sequences, and have the same range. They're not the same because as functions they're not the same. Here's the difference. X of n grabs 1, so I'm out off the screen, but x of n grabs 1. That's the first item in its domain, if you will, if you make it the order set first domain. It grabs 1 and sends it to minus 1. What does y, that's a y, what does y do to 1? Y grabs 1 and sends it to 1. So as functions, they don't do the same thing. Is that okay with everybody? That emphasizes the order. The first term here is 1, and y, the first term in x was
-1.
-1. Is that okay with everybody?
So even though if we were to look at them as sets, sets would be equivalent. But
The range would be equivalent. But the input values are not the sets are not the, the functions are not the same.
I guess what I mean to ask is, like with sets we talk about, like, okay, is the number 3 in this set?
As sets, we'd say they are the same.
Right, okay. So we wouldn't be asking, okay, is 1/3 in x sub n up there? We wouldn't ask that question.
It could be asked that you're asked if it's in the range.
Okay.
But what's important in terms of defining the sequence is that number in the range? Is it an output value? Is it a term in the sequence? And at what position does it happen?
Right.
So what's the order for which that occurs then?
so as long as everything's in the same order, then we can.
And have the same numbers, they're the same.
Sequences are the same.
Yeah, that's right.
So what about sequences that almost have all the numbers, but our one sequence might have a few extra numbers?
They're not the same. So that's what we have. So that's what we think of sequences. They are ordered sets. All right, well, I've given some examples. I want to give a few more. Here's another example. So I can have the set that looks like, the sequence that looks like 2 as n runs from 1 to infinity. So here at Dalton, what's the first term? What's the next term? Next term. And forever it's 2. That's the example. This is the sequence. Let's do another example. Let's say I had the sequence that was called 2 to the n. Audra, what is the first term of this sequence? What's the next term? What's the next term?
8.
Okay. And then I'm gonna put some more, 16, we're just doubling each one of the terms, 32, and so forth, okay? This is the sequence. And I'm gonna put one more. So another example, if I look at the sequence, it's minus 1 time, minus 1 to the n times n. Okay. Mary, when n is equal to 1, what would I get? When n is equal to 2, what would you get? Nope. This part's 1, but don't forget it's multiplied by this.
Oh, 2.
2. Mary, what's the next term?
3.
Almost.
-30.
What's the next term, Mary?
4.
Next one.
-5.
All right. And we're going in this path.
So, could we, or is there a way that we could rewrite that as like n times our x of n that we had before?
Yes, that you can't have the product of two individual sequences, and we can define it in that way, and we will define it that way. Yes. But right now, I'm just saying that's our sequence. So that's the thing. Yes, we can. Okay. What are we interested in by sequences?
Another
Chuck.
question.
All
You did say before that even if they have a different function, as long as the output's the same, they're equivalent.
No,
No.
even if their output has to be in the same order.
So if the output's in the same order and has all the same quantities,
They're the same sequences.
so like -1 to the power 2n plus 1.
So
would be the
here,
same as.
this was an example that Chuck was coming up with. So if you had -1 to the 2n plus 1, and I was looking at it, and somebody says, how would you describe this? Well, the first term of the sequence, when n is 1, this would be -1 to the third, so you get -1. And then when n is 2, so here, when n is 2, okay, I would get -1. When n is 3, I would get -1. Is that okay?
Yeah.
So I'm going to stop there. That's what that is. This does equal to the sequence that is -1 all the time. Just like where we had 2 all the time. So I have two different representations for that sequence.
Okay.
They're the same.
Okay.
Is that okay?
Yep.
Okay. I'm not sure this one did what you expected it to
They
do.
didn't, no.
But that's okay. It did something, and there is something that's an equivalent way of listing it. Okay?
Okay.
Well, talking about the sequence right here, and the one we had that was always 2, lends itself to a definition. So here's the definition. A constant sequence x of n is a sequence such that x of n, the nth term, equals to b for some fixed b in R. I don't have enough room, so I'm going to write it up here. For all n element of the natural numbers. So every output is b. Is that okay? I got it in there, didn't I? And just as a quick example, we've already seen some, but the sequence that is 3 from n running from 1 to infinity is 3, 3, 3 is a constant sequence. Melissa, for our definition we had B. What's B in this problem? In this example? No? B is, B here is, yes, it is x sub n here in terms of the definition, but what is that numerically? What value is it? For our example. So what's the constant number we're getting every time? 3. So that's the output value. B, the output value, is always, for this particular example, 3. Is that okay with everybody? That's what these symbols mean. Another example, if I look at the sequence that's in, John, what do I get out here? What will be first? 2, 3. Is not a constant sequence.
Dr. Whitaker,
Yes, ma'am.
is it constant with a T or with
Yes, with a T.
with a CE? Because I don't know if there's two different ways you were spelling it.
No, oh gosh. No, it's with the T. So here, Audra is nicely making a correction for me. So please forgive me. Here, this should be constant. With the T. Yes, ma'am. Thank you. I was thinking, I guess, about the word sequence. So that's what I was doing. It's not a constant sequence. Thank you very much. Okay, so I was just going in this direction a minute ago about what are we interested in for sequences. And what we're interested in is, do they get arbitrarily close? Do they go to a specific number?
So limits.
Right, we're going to be talking about limits of the sequence. And so it's a big definition. Let me erase here the board and get this definition on the board. It has to do with convergence, and we will say with limits, yes. So this is a major definition. Okay? Major definition. Yes, I'd start too. It says a sequence. Let's give it a name. X sub n converges. That's the word. Is a convergent sequence. Convergence. If there exists an L element of R such that for every epsilon greater than 0, I don't like writing it. I'll write it this way. For each epsilon greater than 0, there exists a K element of the natural numbers such that for all n bigger than or equal to K, the absolute value of x of n minus L will be less than epsilon. Holy smokes. I'm going to write it just a little bit more. That's the definition. In this case, we say x of n converges to L, and denote this by the limit as n goes to infinity of x of n equals to L, or x of n with an arrow goes to L. Give everybody a second to write that down. You know, with our notation, it allows me to say something that I can't not say. Audra, in this case, our sequences are going to L. Only sequences are going to L. In a handbasket, I guess. Thank you very much. I know it's terrible, but that's the type of jokes that I have. That's the only thing I can do. The last joke I told the dean, he said, John, that's totally inappropriate. So these are the jokes I can tell you. To the dean, I tell others.
How do they open?
Open was fantastic. We're going to say what the idea is in a second, but I want to write down one more. I don't want to write down one. We'll write down the idea next. Okay? And then I'm going to play something off of this definition too. One more definition off of this one. First of all, let's get the idea. The idea is this. X of n converges to L. Means all the terms of X of n can be made to be within any specified distance of L after some point in the sequence.
So like in an example, if we look at the sequence of 1 over n as n goes from 1 to infinity, we can say it converges to 0.
Yes, we can. We'll do that. Okay, before I get to that, I would like to write down the symbols that involve this kind of idea. Okay. Here, this is where for all n. These two lines really are being denoted here. X of n minus L is less than epsilon. So the distance between X of n and L are being made to be less than epsilon. So all the X of n's are within epsilon distance, okay? So epsilon is my specified distance, okay? And then it says after some point in the sequence. So it's not that all the terms are within epsilon distance of L, whatever epsilon was given to me. It's after some point. What point is that? That's K. That's what we're saying. And let's look at the example the Corey brought up. Okay? I'd like to do that just now. But first, there is this definition that I wanted to play off of, the definition of convergence. So the definition it plays is kind of an anti-convergent. If a sequence X of n does not converge, we say X of n is divergent. This is a very important thing, whether a sequence converges or diverges. That's what we're interested for a lot of this class. And if it converges, what does it converge to? What's L? Divergence is an important aspect. I mean, my God, they even made a movie about it. Thank you very much. And this is as good as it gets for me. This is it. Okay, I'll do this one of it. It's on tape. And some of you have already heard this show. And for those of you who haven't, this is it. Okay? I don't want to say anything else trying to be humorous. Melissa, can you name 3 cars that start with P? Can anybody else help, or don't ruin the joke for those of you who know it? Dalvin, can you name a car starting with P? Prius. Can anybody else help?
Porsche.
Porsche. Yeah, Pontiac. None of those cars start with P. They all start with gas. I know it's bad. I'm done. Okay? That's it. We're not going to have any more fun in this class. That's it. Thank you for laughing. I know one of the benefits of holding the chalk is people laugh at some things you say. So it's an example. Show x of n, I'll put 1 of n, because n runs from 1 to infinity, converges to 0. That's what Corey said exactly. All these proofs have the same type of format. So here's my well, we've erased the definition, but what does it mean for a sequence to converge to 0? What it means is that will happen if for each epsilon you're given, for each distance that you're given, and I didn't write the definition correctly. Did it say for each epsilon, what did it say? Read your definition. Let's make sure I wrote it down. For each epsilon, it does say greater than 0. Okay, good. That's important. So for each number bigger than 0, that represents the distance. Okay? So for each epsilon greater than 0, we've got to find a k. There's got to be a k, a spot in the sequence, such that from that spot on, all the terms of the sequence distance from the limit point, which the limit point is 0. Less than, not equal, less than epsilon. Is that okay? So here, we need to do that for an arbitrary epsilon. Okay? It's supposed to be true for each one of them. So we just give me one, not a specific one, an arbitrary epsilon. That's the way we start up first. So we let, every one of them has this form. We let epsilon be greater than 0 be given. What am I looking for? I'm looking for a spot. That spot is called k. We need a k. And where is k? I hope I wrote this correctly. Where is it? What's about k? Did I say anything about it?
Such that for all n less than.
All right. In the definition, k, you make this change. K has to be a natural number, okay? I did say that or not?
Yeah.
Good, okay. So k has to be a natural number. When we say it's a natural number, remember that's a spot in the domain of the sequence. So if you think of them as ordered listing of the set, it's a spot in the listing. Okay, the numbers that I put them. So from that spot on, such that from that spot on, so for all n greater than or equal to k, from that spot, k on, the absolute value of x of n minus L is less than epsilon. Let me put in specifically for our particular example what x of n is and what L is. So, we need a k element of the natural numbers such that for all n bigger than or equal to k, absolute value of x of n, what's x of n in this problem? Minus, what's L? 0. Is less than epsilon. That's what I'm looking at. I want to make sure that the absolute value of 1 over n minus 0 is less than whatever number they gave me. If it was positive. They gave me some positive number. I don't know what it is. Got to make this happen. So we're looking for a k. In these problems, we're really going to be solving for n. So here's what I want to say. I'm going to write it this way. We want, so here's what I want. I want 1 over n minus 0 to be less than epsilon. That's what I'm looking to do. Yes, sir, Ed?
Is that greater than or equal to k?
Yes, it is. Greater than or equal to. I want this to happen. Okay? how do I know there's any natural number that can make this happen? Well, let's see. Let's end up solving for n. So here, this means we want, well, 1 over n minus 0 is just, okay, so that's inside absolute value. It will be less than epsilon. Remember, as I write here, and I said in the idea for a convergent sequence, the absolute value of 1 over n minus 0 is really the distance between 1 over n and 0. Is that okay? Okay, so we want this. That means we want, all right, now wait a minute. What can you tell me about 1 over n? What kind of number is it? I've got the absolute values around it. I'd rather not have absolute values.
It's positive.
So 1 over n is positive. How can I get rid of the absolute values? Well, if I know whether what the sign is of what I'm taking the absolute value of, I can tell you what the absolute value of it. It's either itself or it's minus itself. 1 over n is a positive number because n is a natural number. So the absolute value of 1 over n is itself. Is that okay? So I'm just kind of breaking down what it is that we want. We want 1 over n to be less than epsilon. And remember I had said we want to solve for n. Okay? So we want, solving for n, I'm going to go real slow. I'm going to multiply everything by n. And n is a positive number, so I won't have to change the inequality. The 1 will be less than n times epsilon. I'm going to continue on in this fashion. So we want, if I multiply both sides by 1 over epsilon, and epsilon is greater than 0, so 1 over epsilon is greater than 0. Epsilon isn't 0, so 1 over epsilon exists. What we have is 1 over epsilon is less than n. That's what we want. Listen, that's the last time I'd be that technical. I mean, how do you solve 1 is less than n over epsilon where epsilon is positive? How would you solve for n? You divide both sides by epsilon. That's all. I'm going to start saying it that way. We're not going to get that technical again. Okay? So that's what we want. How do I know that there's any natural number that's bigger than 1 over epsilon? What if epsilon was 0.0001? 0.0001. I think that means 1 over is like 1,000 or 10,000. How do I know there's some natural number bigger than that?
It's not bounded with 1 over.
Because the set of natural numbers is not bounded above. What's the name of that theorem? That's right. So by the Archimedean property, so 1 over epsilon is not an upper bound for the natural number, so there's a natural number bigger than it. So I'm going to say there exists a k element of n such that 1 over epsilon is less than k. So there is some natural number bigger than 1 over epsilon. I'm going to call it k. Is that okay with everybody?
So is that the set n?
That's the setting, yes. So I guess I have been noting for that. Scripting, that's right. I'm almost done. So here's what I'm going to say. Look, if this is what we need to have happen, we want n's to be bigger than 1 over epsilon, and I found one natural number that's bigger than 1 over epsilon. Every natural number bigger than this natural number, if you're bigger than this natural number, you're going to be bigger than. All right, so thus, for all n bigger than or equal to k, 1 over epsilon will be less than n, which is what we want. I want to say, I want to take just a minute more, okay? I'm sorry, I'm put some of them out of class. For me, this is a good enough proof. I'm done. For others, and I'm going to do it just one time, they say, hey, look, you didn't satisfy, you didn't show. You've given me a k. It's the k that's bigger than 1 over epsilon. But really, you didn't show that, what was the statement? That 1 over n minus 0 inside absolute values will be less than epsilon for all n bigger than or equal to that k. So they'd have me work backwards, the ones that are sticklers, and some of us are. So Dr. Menders in particular would say, John, come on, you have to show this other part. Whereas my teacher would say, you've done it, you've shown your work. Some people would say what you've done is the scratch work. So here's what we would end it with. I'm not going to ask you to do this, okay? But I want you to be aware. So, for all n bigger than or equal to k, look, I got this. 1 over epsilon is less than n. Let me just write that down. So, for all n bigger than or equal to k, this would say that if I multiply both sides by epsilon and divide by n, the 1 over n will be less than epsilon. Is that okay? I multiply both sides by epsilon and divide by n. That's what I did. So for all n bigger than or equal to k, the absolute value, 1 over n minus 0 will be less than epsilon. So for all n bigger than or equal to k, the absolute value of 1 over n minus 0 will be less than epsilon. And they say, hey, there, now you've shown that the terms of the sequence minus 0 inside absolute value is less than epsilon. But I just worked backwards from what I did. So it's not needed. Okay? But some people say, we like you right there. I don't. This is the work. I found the k that's needed. Okay? I'm going to talk about that in more detail next time. We'll do more examples. We're going to have some facts having to do with convergent sequences. And that's what a large portion of this course is going to deal with. Thank you very much.